Hello, engineering statics students. This example problem is on the topic of friction. And for this, we're going to use our well-known equations of equilibrium, lots of free body diagrams, and we're also going to use the concept of imminent slip for a static friction situation to give ourselves extra equations to solve for what we want to know from our free body diagrams. So we have a stack of books, and someone is holding these books up, and they are able with their hands and their muscles and their arms and chest to exert 120 newtons with each hand on this stack of books. And the coefficient of friction between the hand and the book, which would apply only to these end books here, is a little higher than it is between book to book. So hand to book is 0.6 and book to book is 0.4. We're given the mass of each book and we're asked to find how many books you can lift without the book slipping. So the key to this problem is, believe it or not being super concerned about friction per se, but by focusing on drawing the free body diagram that is going to lead us to what would be called the limiting case for our slip. So to do that, we have to just step back and go back to our general equations of equilibrium and our free body diagrams and look at what's happening to the whole system. But think in terms of, I can draw a free body diagram with any number of books in hands, one book, all the books, because everything is in static equilibrium. So it doesn't matter if I draw an FBD of 6 books together, I can pretend they're welded together because I'm going to establish a condition of equilibrium that says nothing's accelerating. So if all 6 books aren't accelerating towards the floor, 1 out of 6 is not accelerating. I will impose that and then see what conditions are needed to keep all 6 from going down together. And then I can make sure that is bounding to what would be needed to keep any one book. So I'm going to start by looking at all books. FBD. So I've got all the books. I'm going to say this is N books. So if I put those all together, I'm going to have a weight force acting on them. I'm going to have 120 newtons pushing to the right with the person's hand, and the stack of books is not going to accelerate to the right because the person who's holding the books is going to apply 120 newtons with their other hand. So we have a trivial equation of equilibrium for the x. We know we got 120 newtons going in both directions. And more importantly, we know we have a frictional force hand on book, and we'll call it FH for force of friction hand on book. And we have one on the other side too. We can apply action and reaction to each side of this stack of N books and know that we can invoke imminent slip to solve for our F sub h. And so we can say that the normal force that would apply in this case to the hand and the book frictionally is the 120 newtons. My hand is pushing on the side of the stack of books with 120 newtons. The books are pushing on my hand with a normal force of 120 newtons. So our normal force, which would go into our imminent slip frictional calculation, our max frictional force, hand to book, we'll use that 120 newtons. And let's go ahead and put some units on these 120 newtons. Moments not going to factor in. It's a symmetric system and we don't have the dimensions to calculate it anyway. But we'll call the weight W sub n. We do have a sum of the forces that we can define in the y, and that's going to be key in all these cases. So we can say the weight due to n books minus 2 times the friction force, hand on book, has to be 0. I can give myself another relationship. I can say imminent slip. We're going to assume we're just about to slip that stack of books right past your hand. So that says instead of 2 F sub h, we have 2 times the book on hand frictional force times the normal force, book to hand normal force. And we know that Wn is the number of books, n, times 0.95 kilograms times g equals 0. So we can solve this equation for n and get the max number of books that we could hold between our hands, assuming that the books aren't going to slip past each other, but that they might slip at our hands. And we'll just get a number for that. So we'll do a little algebra. So we have 2, enter, 0.6 times, 120 times 9.81 divide, 0.95 divide, and we have n equals 15.45 books. And we would of course round down to the nearest book below, so n equals 15 books. Okay, so if the books couldn't slip between each other and could only slip at your hand, you could still only carry 15 books. So, and they would slip right here. So they would slide right out of your hands. Okay, and so that flowed from us constructing in all the books FBD and imposing the conditions for book on hand. Okay, well, I guess we can also take another case, which is kind of bounding in the other direction, and say, what happens if we just consider one book? So let's take this guy in the middle here. Let's just look at this one book. So we'll do one book, FBD. So here's one book. Again, we've got 120 newtons because our compressive force was not attenuated. We didn't have any strain in any of the books. So these are rigid bodies. So basically, if I'm pushing with my hand 120 newtons, these 3 books to this side would push back, and the middle book is being pushed on by those 3 books, and etc. We could apply Newton's third law, book to book to book, and we would find that that middle book is being pushed on. It's subject to the same compressive force that the whole stack is. So in this case, we've got a frictional force of friction book on book, F sub b, book on book friction force. And we've got a weight that is the weight of, we'll call it W1 for one book weight. Again, we can define some of the forces in the Y. So we've got weight 1 minus 2 times book on book frictional force has to equal 0. I know what this value is. It's just simply 0.95 kilograms times acceleration due to gravity. And now I can define this term as 2 times our normal force, which is 120 newtons, times the book-on-book coefficient of static friction, which is less. So we've got a different situation here. And that has to equal 0 to keep that middle book in static equilibrium. Okay, well, one book. Didn't really get any information out of that. We could make sure it equals 0. Or that we didn't get any information about how many books we could hold up because we chose one book. But we could make sure that this weight force is not any greater. Imminent slip means book's going to slip. I put that in. We may not have needed this entire amount, and that's something I should have pointed out. I declared imminent slip without knowing if I was even going to need it. I was going to get close to that because I've already defined my weight, but let's just calculate it out, make sure what the weight is. So the weight of one book is 0.95 kilograms times 9.81 times. So one book is about 9.4 newtons. And our imminent slip condition would provide us with a frictional force of 120 enter 2 times 0.4 times 96 newtons. So we can hold up more than one book, that's for sure, because imminent slip in this case would give us a lot more potential frictional force than we needed for that one book. So could we extrapolate on this and draw an FBD that encompassed as many books as we had frictional force to accommodate, and keeping that book-on-book situation going? So if we can draw a one-book FBD, well, we can use that same approach to calculate multiple books. So let's take all the books other than the two ends. And the reason I'm not taking one of the end books, I'm taking all but 2 instead of all but 1. If I took 1 against the hand, I would have a different coefficient of friction, and I might end up with an unknown I can't solve for. So we can discuss that in brief, maybe right at the end. But for now, I'm going to assume the total number of books that this guy is holding is the n over here. So by taking only everything other than the n's, I have n minus 2 books. So I'm going to call it weight n minus 2. And we've still got 120 newtons of force in the x direction on both sides. It's still symmetric, which means the normal force for frictional calculation on the book-on-book on both ends, book-on-book friction, F sub B, is going to be based on our smaller 0.4 mu sub s coefficient of static friction of 0.4. We can do a sum of the forces in the y on our all but 2 book FBD over here, and we can say the weight due to n minus 2 books minus 2 times the book-on-book friction force has to equal 0. And this term is going to be n minus 2 times 0.95 kilograms times g minus 2, and the book-on-book frictional force, now we invoke imminent slip. At imminent slip, I get the normal force times 0.4 mu sub s for book on book, and that has to equal 0. Now I'm going to isolate n sub 2 with a little algebra, or excuse me, n minus 2. So we're going to have 220 times 0.4 times, so we have 96 newtons on the other side, 9.81 divide 0.95, 0.95 divide, so n minus 2 books equals 10.3. So n equals 12.3 books. Well, if we don't want it to slip, it has to be less. We have to round down. So this tells us that n equals 12 is the most books we can carry. Okay. This number was valid for the conditions we considered. If the coefficient of friction between the books here had been big, what if that had been 0.8? This is a linear relationship. This number would have doubled, and we would have been limited to 15 books. So this is one of the twists of friction problems, is that we can end up with something that is true, but not limiting. So pause here and get back to the whiteboard. Okay, we're back with a little pause. So we've concluded that based on the relative coefficients of friction, static coefficients of friction between book on book versus book on hand, the book on book case is limiting, and we will only see the effect of that when we use theoretically as many books as we can, which we achieve by using this fuchsia n minus 2 total books FBD. So this is the n minus 2 FBD. Okay, so this one gave us our limiting case. Okay. So one question that might get raised, and it's a legitimate one, is why couldn't we use an n minus 1 FBD and use friction on one side, hand on book, and book on book on the other side? And the reason why we couldn't do that, and it would have given us a different answer actually, is we would have had something we couldn't actually solve for. And we might have been tempted to make an assumption about what that was, but we wouldn't have really actually known it. So I'm going to do that in an orange here. So say I had decided to use this orange FBD, this orange set of books. So here we've got all but one book, and we've got a hand on one side and a book on the other. So if I were to FBD that down here, I would have n minus 1 books. I want to have weight n minus 1 equal to n minus 1 times 0.95 kilos times gravitation, acceleration. I've got applied force from a book on one side, and I've got applied force from a hand on the other side, leading to 120 newtons of normal force. And I have a frictional force book on hand on one side, and I have a frictional force book on the other. So if I write my equation of equilibrium in the y direction, I would have to say frictional force of book on hand minus the frictional force of book on book. I'll make those positive. Minus n minus 1 times mg for short, equals 0. When I apply imminent slip, I'm going to get a value for this one. This will end up being, this is limiting. So I'll say, okay, you can only get this much, 120 newtons. The problem is you haven't really defined how much this one's giving you. If you knew exactly where things were being applied, maybe you could figure it out with a moment equation, but at the end of the day, we don't really know what that is. So we cannot, as might have been done in an earlier solution to this, just simply assume that it's the same. That's something that's really tempting to do, and it leads you to get a little bit different answer. It's close. It certainly is going to be closer than using this over here. But at the end of the day, we can't be exactly sure what this is applying. We know that it would give a max of, it's capable of giving us 0.6 times 120 newtons. So obviously it's not going to give us that much. To be fair, maybe it would give us something close to what our book-on-book F on the other side is giving, but really it's all going to depend on moment, exactly how your hands are placed, and is something a little bit off the center axis. So that's not particularly solvable without enough information to have another equation. So we basically don't have enough in that case. And this, we would have an unknown in the form of n, and then we've got an unknown in the form of f sub b, and an unknown in the form of f sub h. We can take care of f sub b with imminent slip, which would then, if we knew f sub h, allow us to solve for n, but we don't have that. So we have to go with our former fuchsia, book on book, all but 2 books, and be content with 12. So that is it for this problem. Key topics: continue with standard equations of equilibrium, and write or construct sufficient FBDs to capture your limiting case. And as a good rule of thumb, make sure you've captured all the different types of frictional interfaces. Assume something could slip at one interface, maybe it could slip at another if you're not sure. And in this case, the question is asking us for a maximum. How many books? So we got to assume any of those interfaces could slip. We're not sure exactly which one is going to go, so we basically went through and tested them all. And by adding books to the book-on-book frictional case, we basically allowed ourselves to solve for as many books as needed to exceed our imminent slip condition with our one equation of equilibrium. So that is it for this friction statics example.